Assalamualaikum and very good morning. So today is really the our third class of revision. Actually, today is a revision class for our end term exam. So end term exam, we have actually we have to cover the end term exam today is end term exam. So have two topic in the exam. Sorry, is thermodynamics thermodynamics and plus another one is magnetism. Magnet- Okay, so they have two question, one question in magnetism and one question in thermodynamics. Just two questions. So today I try to cover the two question and try to give you as best as possible hints or techniques or actually just to revise back what have we done, what we have we go through in the mechanism. I think all the notes is available in the portal, one that I already told you before. One more thing that I have to ask to tell you that we provide the equation in the exam. So you may just didn't need to remember the question. However, you have to know how to use the equation. Which equation is for which solution or which I mean which equation for which question that you need to do. Okay. Okay. So we start from previously. Actually, we know that the magnetism actually have also the beginning is electrical field, where that we have electrical field is come from the force of the charge is from the electrical field, but then magnetic field itself B, now it's a B, is magnetic field come from of the force and the charge itself and also the radius. You can also mention force actually is equal to charge velocity cos which the this one is a cross product. This one actually we have go through before. Then I also mentioned to you previously the one to make to if you remember right hand rule. So I can put here right hand rule. What is right hand rule? So if you have, for example, this one, like and we have the current flow in this direction. Using your right hand rule, you can find that this is the direction of the current, and you're using your thumb like this. I mean, maybe I can try to again draw the my beautiful hand just now like one, this one. So yes, so this is the direction of the current. So this is the direction of the this direction of the current. Your eye, and this is actually the maybe I can change the color. Direction of your magnetic. This one. So this one is your B. So for this case, you can find that your magnetism, if this is the direction of yi, this is your, so your magnetism actually is your magnetic field actually in this direction. And you can find that this one actually, the magnetism, actually this dot show that it's come out and this one actually go into. So let's go into the page. So into the page, this one actually out of the page, and this one maybe I can put the yellow color. This one is into the page. Okay, and rule. So we can have something like if so from that we can also get the magnetism field B is equal to mu naught, actually mu naught I is equal to over 2 by R, because R is the rotation. Like previously we have discussed that how that the B becomes R rotation itself. I mean, so that's why we can have this one. So for example, if we have a question, I think if you remember, if you have the question that a vertical wire, for example, some question if you have something like a question that we have the wire, and then that we can have the current here goes to here I, and then if the current goes to here using your right hand rule, so using your right hand rule you get the magnet, the B actually now in which direction, in this direction, so it's in this direction, so something like this direction. Then we can have this direction, so mean that the actually the come out from here and go inside from here. Then we can also using this one. You can calculate if you know this, if you have something like okay, the B actually is here. I mean, for example, we can here actually is something like if B is placed in here, I mean here, sorry, is here, B, so you can have something like this is the value of R, direction of R here. So, for example, if we know that uh, this one is something like okay, the second question we have something like this one is 8.10 times 10 so we can have something like mu naught I over 2 pi R. So and then we can have something like mu naught actually is we know this one actually have okay, go forward then okay, 8.0 and 10 of 1 over 4 Tesla. Mu naught is 4 pi times 10 of power. Remember? Then we need the IA if given by I, for example, here is 25 M, it's 30 IM, so we put just 35 M, the I in M, so 2 pi and R. We get the you can get the value. How to find the R? The R just given this one R here, so we can just R is equal to 4 pi and 10 of minus 7 is 35 M divided by 2 pi. We have 8.0 times 10 of minus 4. Then you can get the R. Same thing if you have the if you given the if you have also given the value of R, where is the R? Maybe 2 cm from the wire, so you can just get the what is the magnetic field. So you can just using this B mu naught I 2 pi R. So then you can just fill in the mu naught I, and then you need also the value of I. What is the I? So if I is, remember, if 2 cm, we need to convert into meter. So 2 cm is equal to maybe 2 times 10 of power minus 2 meter, or you can also have 0.02 meter. That's the conversion, so that you can have the the value. Then I also introduce you the force. Actually come from the right hand rule again. So we have the right hand rule extended, right hand rule, maybe I put it extended. So in right hand rule extended, I mentioned you get, we have the, maybe I can change palm. Then you have the, this your hand, something like this. So maybe the red color here. This one's still a current here. But then this is one is the magnetic field, the B. And then this one, your pump itself is the force. So now it's become like this. It's become like, if I draw, it become like I. This is the B, and then this is a F. Is all the 90 degree each other. It's something like this. So this is, sorry, this one is 90 degrees. So like this. Yes, so like this. So this is the direction of the force. So for example, we have the wire just now. So for example, we have the wire just now. We know that the direction of I is this one, I this one, and B is sometime just now. Maybe you can put this one. Our B is here. So we can see that the I and the B is go inside here, go inside. So maybe the direction of force. What is the direction of force? Is here. F is here because B, this is B, is into the page. And we can get the force actually go toward the the on the left. This how that we do for the force direction. And then we know that the formula is given to given by F is equal to I L. So L need to L B sine theta. So I is this one, the current one, that this one. I is the current, the one that we have. This one is the I. L is the distance of the wire. D is the L, or the length of wire. Length of the wire. And then we have, and then we have B is the magnetic field. And then again, we need to know the sine theta. What is the sine theta? Sine theta actually is, okay, go on. Let me check the, let me see the record now. Okay, still early. 40 minutes. Okay. The sine theta is is theta that I and B. So we have, for example, this is one B, the magnetic field, and the I is F I. This is the sine, this is theta. So for this case, I and B is almost this one. In this case, it's 90 degree. So sine 90 degree is equal to 1. So here we can get F is equal to ILB. And then if I here, for example, we can put this 25 M, and then we have a 25 M. Then since that we can put this one is 10 cm maybe. So 10 times 10 of power minus 2 meter. So at B maybe here we can put back the just one. Now we have 8 Tesla. Okay, we can put the 8 Tesla. Okay, you can get the 8 Tesla 8.0 times 10 of minus 4 Tesla. So then we can get the force needed. So if B and I is a parallel, something like this in parallel, so sine theta is become sine 0. So it's become 0. What? Then force become 0. This is actually to be more. Okay. And then maybe I can further discuss with you about the I. Actually, I itself, I actually Q divided by T. You Q here actually is this is big Q. So the small Q actually the charge, the number of charge. This is number of particle. So this is number of particle, and then this is single charge. This is just single charge. So single charge divided by T, the same thing also. And then we have the velocity previously. The velocity given by distance time over time, and our distance can be velocity times t. So we can have something like L here just now. Here L can be a Vt in our new derivation. So if F is equal to Qn over T, and then we have the actually the equation F equal to RLB, we assume that theta is 90 degree, so sine theta become 1. So Q I is f Qn over T. L now is Vt. T is now L. It's become V times T. Then Q, I, L, and B. B is the normal B here. So we can put also sine theta here if you want. So T here can be simplified. And then we can have N actually is the number of charge. So we can also have Q BQ. We can have the Q BQ Q V B sine theta, or we can also have in term of N Q the charge V B sine theta for the force. Or we can have also even for a single charge. So if for single charge, single point, so single point charge, single point charge which and one, F is equal to QVB sine theta. This is a new V. This is a new, maybe this is a new formula for single point charge. Can have the force for the single point charge. This actually can go towards moving of photon, so we can now discover oh sorry, moving of proton or electron. So we can have the charge of proton moving here, and then we can have the again the same formula here. Sine theta here, for example, this sine theta here. Previously, we have the sine theta from the I I so I this one and B, sorry, okay, from the I and B, this sine theta, this is theta. Now in this equation we don't have any I. We already changed the I with the charge. But then the charge actually is the moving now. The charge is moving. So if the charge moving here, so we can consider that the moving particle. Now this is charge actually come from the I itself just now. So this charge here actually the Q, the moving charge, theta actually calculate from the moving particle. So for example, if the moving particle in this direction, so if the magnetic field, so the moving particle, so if moving particle is in the velocity, and then we have the magnetic field B, theta is calculated by this one, the direction of particle, direction of particle, which the magnetic field B. So this is theta. Then we can use this formula F is equal to QVB sine theta. Same case, the only thing is actually different avenue. Okay, we have actually show you the proton move with the speed, something speed, and then we can calculate the its. And then one more thing that you have to know, that when we have that direction of force, I mean, if you have the charge of, for example, you have the magnetic field here, this position like this, and then you have the particle, your particle itself. I mean, your particle itself here. This one actually particle itself. Your particle actually moving in this direction, which is actually perpendicular to the, so sine theta is now, sine theta is sine 90 degree, which is one. You can have the formula B. The most important thing actually is you have to using your right hand rule. So you can see that your right hand rule mention that when your force moving in this direction, so this your velocity, and then so we can see that, okay, using the right hand rule, we can see that the force actually acting on the which direction. So this is as the current. Now V as the current, so this is your thumb is like this. So maybe I can draw the thumb like this. You have thumb like this, so you have, and no, maybe so your hand is actually pointing into the page. The force actually into, so it's something like the into the page. So your V here, so the force actually in this direction. Okay. So what happened when you have the force? So you have the ball moving in this direction, but then the force actually acting on that direction. What happened? The ball actually tend to be turning back. It happened that the ball will turning back, turning, and it's become a circle. That's why if in this condition, when the actually this why that the magnetic field, when you have the current moving in this direction and you have the magnetic field moving in this direction, something like that, it's really because of this part, because of this one. If you look into the particle of psi, we can see that they are moving. If the current actually here moving here in this direction, then this have the particle moving. So you can have something like this formula, and then you can have something like the R value, what is the radius of the rotation. Okay, yeah, I don't need to go further because we have also, and then we have find that the R actually the moving one actually can be calculated by and B is divided by B. This is the formula that I think you can look around back to the our sample equation I have give to you. So you can have get the value of rotation. I mean the radius of the rotation. How big the rotation? Okay, and then I think I have to see. Let me see the. But let me see back the. Okay, what the time now? I have to make another story. So we need to know what the time now. Oh, video. Okay, the video now is okay, it's half an hour. So maybe I can go to the second check part. Hope this cover for also finding exam or also enter my exam. We have also okay. I have to cover this one also. Actually, when we have the two wire here, the two wire, we have the two wire. Oh sorry, I have the two wire. So another one, this one, like this one, two wire. So if the I in where I can draw a little bit more. Sorry, so we can draw more good picture. Okay, we have the two wire each other, and then if the I actually moving, so they have current moving each direction together. So you can have something like the force actually pointing each other. You can see the notes previously. Actually, we consider one point when the magnetic charge here, current here, we can have something like the charge actually, the point just moving in this direction. So when we get this direction of the point, we know that the magnetic charge actually here, and then we see what is the force. If the current moving here, the B is pointing here, we can see that the force actually pointing in that direction. And also the same thing also if the force actually pointing on this direction. If you do around for the force here, then we can see that the force is pointing on this direction. And then we can have the force, second force calculated by F2 is equal given by I2 L, and B actually is the B1 because of this B1 B1 sine the uh, sine theta is equal to 1. This one is 1, then we can have the formula is equal to F2 is equal to I2 L, the length of distance, and then 1. And B actually B1 is equal to mu naught I1 over pi R. This I B1 can be further put in there, and further put in the F2 I2 L, and B1, this one actually is a mu naught I1 over 2 pi R. So here you can get that like the F2 force of F2 actually was I2 times I1 L mu naught and divided by pi R. Okay, also another formula that need to be understand. Okay, sorry. And then the last part, actually the solenoid part, I need to also explain the solenoid. We have the magnetism B is equal to mu naught I over 2 pi R. But this is for wire. But the solenoid, we have to formula using the formula is equal to, we can put the B is equal to mu naught N over I. Then N here actually is equal to N over L. This is the loops number of loops, and this is the turn. How many turns? Turns. Oh no, it's turn. It is meter length or length of the turns. So for solenoid, actually, sorry. So the solenoid, uh, how to go back? Okay, solenoid is like this, something like that. The length F N, and then also the number of. Okay, I think that's all. I then we can also have also I not cover this one actually the torque. in even in final exam or also in NTEM exam. So I will not review this one. So okay, I go to the a few things. Okay, we go to the thermodynamics. So thermodynamics, what we have to understand thermodynamics. Okay, the last thermodynamics. Oh, we got the thermodynamics. Start with the thermodynamics. Okay, we have the question about the system. I think I have last class. In the last class, I have to discuss with you. And to discuss two questions. You can open the question first. Let's hold on. Maybe I can open the question. Okay, sorry. So we continue back with our class just now. So let's some break for me. Okay, I have actually asked you to solve. I mean the question for I think, and also have get also some message from your friend asking the question about the two questions that I left to you. I mean this one I think I can also copy here and put it on this our notes just a bit for revision. So the two question actually here actually this one. So maybe it can be more bigger this time. Okay, bigger. I can have, okay, number two one. This one is number one. So, so I need to be bigger with all this thing. Okay, you have to bigger a little bit. 20 maybe. Okay, so this one is bigger. This is actually the assignment. Okay, metal no also something. So okay, question one, and this is question two. How small energy is required to heat 75 kilogram ice from 30 degrees at, if I'm not mistaken, this question is actually why we're not using let me hold on, let me check the uh, question from your friends. Okay, so sorry, I have to see by the question by your friend. Actually, asking me about why we using this value is here. I think in the I think this actually the notes in my notes. I open back this note. So actually, why we have 4186. The question is actually can maybe can go back. The question actually here. How much? Okay, I can put into the revision back. Control A, Control C to the revision. Okay, we can start from this question first. Okay, this asking by your friend. Okay, sorry. So I will just want to move further. We can. Okay, I can move this one. Okay, here. Okay, let me route this one first. This one I know it is okay. It is. Sorry, that was one and also this one. Okay, here. Okay, let me take this one. Go to more further down. It's more easy. The question is basically how much energy is required. Here is the question. So I can put back here. So your friend actually required to convert reason. This is actually the last question. Energy is required to convert 3 kilogram of ice into 0 degree of water, ice of 0 degree to the water at 30 degree. So the asking question why not using the solution just now here actually we are using okay I made the solution like this. So let me again check with the solution then after that I return back why not use the question. Okay, so first of all actually we know that the conversion actually from the uh, change of energy. I think the question is how much energy is required to convert 3 kilogram ice to water. So we know that the ice melting point. So ice to water, and then the water to the another water, which the temperature now is 30 degree, and this is 30 degree. Although this one actually, uh, sorry, is 0 degree of water and this 0 degree of ice. So the melting point of ice actually the melting point of ice is 0 degree. We mean that the ice will change to the water at a 0. Then we know that also the boiling point is 100 degree. This is the boiling point where the water become a vapor or become the gas or vapor or gas, something like that. So it's 100 degree. Here, in here, this is ice to the water, which is same degree. So we can use the Q is equal to ml. Here, from here, we can use it Q is equal to M C delta T, the change of temperature. But C here, the C here actually is C of water. C of water. It's not C of ice because this is the water. It's the change of the water. So this is the change of water. It's not the change of the ice. So you have to understand that the starting point here at the 0 degree. Here the starting point is 0 degree. It's at the melting point. So it's essentially that the temperature is maintained. So if I draw the diagram, maybe if I draw the diagram, temperature heat diagram. So if I draw the temperature and heat diagram, or maybe I have more further down, so before that we can also discuss this question. Okay. If I draw the temperature heat diagram, so this is temperature heat diagram. This is temperature and this is heat. Heat on. Okay. We can find that the starting point is something like, okay, 0 degree here, for example, 0 degree here is the main thing like this first, and then the temperature increase. So here, here the process is equal. Here the process is Q is equal to ml, and here I mean the film color is from this 30 degrees, so maybe I can write also this one is a 30 degree, so it's equal to sorry again. Okay, Q is equal to mc delta T. But here, this part, maybe the green color better, is water. That's why the Cp here, C is here actually Cp of water, not the ice. That's why the value is 4186. We know that previously, and in my class, I have also write that Cp is actually for water, for the water itself, for the water is so the Cp for the water is 4186 joule per kilogram per degree, and then for ice 2100 joule kilogram per degree, and also for the steam itself, the steam or vapor is equal to 2010 joule kilogram per degree. So that's why I use in here the formula here, the charge here is the question actually when the question how much energy required to convert 3 kilogram of ice 0 degree to 30 degree using this formula. So the first actually we have, I can answer back. So Q is equal to ml. So M actually the mass 3 kilo. So we have 3 kilogram. So we have 3 kilogram here, 3 kilogram. And our L here actually we have using the, oh, forgot the L. So I think L have two L. The conversion from the have uh, have maybe below here this question. Okay, sorry to answer your friend question. So L here actually have LF. I put the LF is equal to 3.33 time of power 5 joule per kilogram, and then we have the LV for the vapor one 22.6 time of 5 joule per kilogram. This one actually conversion from water to vapor or steam or whatever. This one vapor, and this one is a vapor LV. So this fusion one actually, if you're using bubble boil, see the fusion power. I don't know. Maybe. So this one actually from the ice to the water. Based on this question, this L actually this fusion L. So we have, okay, I can answer here. This one Q is mass is 3 kilo, and the F is 3.33 time power minus time power 5. Sorry, not minus 5. QL, so we get the value uh, that is we get about 9,999 joules. So, and then the second one actually the one that the second stage, this one. So this one, this Q1 I cover for this one, Q1, and then Q2 this one. So Q2 actually we have same formula, MC delta T. So M is 3 kilo. Our C now is water. It's water now. 4186. Delta T is change of temperature from 30 times 0 is 30 degrees. So we get this one also 376 7,740 joule. Total actually is the Q total. Q total. One that conversion from this charge is about 1,375,740 joule. This one actually What's changed? Okay, let's go through this question. Okay, this question actually this is Q1 and this is Q2. The Q1 I have time a bit. The Q1 actually we have to separate for ice from 30 degree to steam to 200 degree. So the fusion stage, okay, maybe I can change this one. Promote carefully here. Okay, like this one. So we start. Okay, maybe we start from here. Okay, I can start from here also. Maybe we can start from this is minus 30 degree, 30 degree. So it start from the 30 degree to 0 degree. So this have 0 degree, and then we have the another one, and then this 0 degree from 0 degree to some stage to 100 degree. So we have something like this one, 100 degree. Then the stage actually boiling or vaporization, and then after that go to the 200 degree. So our stage something like, okay, this one come to about 200 degree Celsius. This is our temperature, and this is that we okay. From this stage we have okay. Now we know that we have to identify first this one. So Q1 is what? Is change of temperature. So it's actually MC delta T. The C here is actually the sea ice. So this is sea of ice. And then we have another one. Maybe we can change the color. This one is Q2. So Q2 is equal to ML. But here 0 to 0 degree actually is from this is the state of I have to color. I mean this state is water and this state is ice. So this one actually a fusion. Huh? Fusion. So this one with ML. And then again we go to the next stage. Maybe I can color the yellow color here. So the next stage actually is here is Q3. Again the change of temperature from 0 to 3. The Q3 is actually change of temperature MC. Now C here is C of water, delta T. Because this is the state of water. All this one is the water. This is water, sorry. Change the color. Okay. So okay, this is state of water. All this one is water. So this is sea of water. And then the another one is this one Q4. So Q4 is now is M time L. So this one is water to the gas or to the vapor. This is a vapor. Now this is a vapor or gas or whatever here. And this is water. It's water. Change of here actually this head is of vapor. The vapor one. So this Q4. And the last one actually maybe you can put what color? Green color. Maybe the green color here is this one actually Q5 is actually the mass time the C and the delta T. The C here is C of vapor or whatever is you can see that. Yeah, I think we go to the here C of steam, whatever. So if you put all this together, I have to. no time here. I think we have very short time. I can cover another question also. If you look at Q1, Q2, Q3, Q4, and Q5. So maybe Q1 I can write the question. The answer Q1 is what? M is now M is 7.5 kilo. So Q1 is 7.5 kilo. And then change from 0 degree to MCC of I. Of I. So we have to calculate the C of I. C of I is 2100. So we know this one just now. Okay, 2100. Let the change of temperature from 0 minus 30 to 0 to 0 minus 30, 30 degree is to Q1, and then I didn't calculate. You have to calculate because it's too short of time. Q2 actually M of diffusion, so still the 7.5. Diffusion is actually 3.33. Yeah, 3.33 time of power of 5. The Q3 is now change of the water. So 7.5 again, and then the water is forward exit, forward exit. And then the change from 100 is 100 degrees, so 0 volt 100 degree. Again, the also the heat vapor Q3. Q3 is Q4, sorry, Q4 is vapor, so M is still 7.5, and the vapor is bigger, I think. Yeah, bigger. 22.69 of power of 5, yes. And then Q5, the last Q, actually the change of temperature. So MC delta T here, Q5 here, here, this one MC delta T from the vapor, still 7.5 here, but the C here is speed of vapor, 2010, and then the change of temperature from 200 to 100, 200 degrees to 100 degrees also. You can get all the value, then the total up the sum up. Okay, question number one. Question one. Sorry, question one. Now we go to the second question. Okay, second question. Second question actually asking you. Okay, this is the part I have to cover this one for you. Okay, the 0.24 kg hot metal at 150 degree was dropped into the beaker containing 0.5 kilogram of water at 21 degree. The final temperature of the measure was found to be 77. What is the specific heat capacity of the metal? So here actually, okay, we have the beaker. Okay, let me see. I the beaker. So the water is a blue color here. Okay, the water. The initial temperature of the water actually here is given by okay. So you have the mass of the water have mass is mass 0.15 kilo, and the temperature is 21 degree. Temperature 31 degree. And then you have the hot metal. So the hot metal. Hot metal. So was actually 150 degree. This one is the temperature is 150 degree, and then the mass is a 0.24. Okay, the mass is 0.24 kilogram. What happens? This metal is dropped into the water. So what happened? It's become like this. Water here. You have water here, and then you have metal inside here. Now the metal is inside here. The water will be. And the final temperature is 27 degree. The final temperature when the heat object enter is 27 degree. Oh, sorry, I can write in the wrong color because it's water. Okay, 27 degree. So which actually here show you that the initial the final temperature, the heat actually they actually move out. So this heat actually may move out, and then so we have so the Q meter, the temperature. Okay, maybe I can write in the one. So here, now at this one, the Q metal is equal to the Q water. So they are asking for the what is the specific heat capacity of the metal. So we have the, so you know the specific heat of the water. So the Q water is given by MC. Oh, sorry. Sorry for this one. So let me again one. Okay, C MC delta T. We know that the specific heat of water, C water of water is 416 joule kilogram per degree, and then it's given of mass of the water is 0.15, so it's 0.15, and C is given to you is this one 4186 4186, and delta T is the temperature of the chill water. So what the change of water? Water change from the 21 degree. The water is actually changed from 21 degree into 27 degree. So something like 27 minus 21. So it's 1 or 21. If you calculate this one, it's actually 0.15, and you have 41x, and this one is 31 just then you can get about, I don't know, but there's almost something like 400 something, 400 I didn't calculate very well, but I think it's this one. So this is the charge. And then we know the Q of the metal, Q metal, the same thing. So it's actually M C delta T. We want to find the C. So mass of the metal given to us, the mass of metal is given to us is 0.24 kilo. So it's 0.24 kilo. And the C we have to find C of metal. And delta T is the temperature change from just now initially is what is 150 degree become 27 degrees. So it's 27 minus 150. 7 minus 150. Here the Q of water actually is negative because here the heat actually go out, not go inside. So you can see that the Q heat Q here this Q metal actually negative is Q water because the heat go out from the metal is positive, but heat for the water actually go inside the water is Q negative. So that's why here actually is minus. Okay, but then you can actually when 27 minus 100 minus 150 you get something like some negative value. This can see as so here actually you can just this one is equal to this value, this value. So minus 439.3 joule. I didn't calculate very well, but you have to calculate. I just to show you this one 27 minus 20, and then you can get the C, maybe about 148 148.9 joule kilogram per. So this is the C of the water. You can find that, okay, you know, you get the value. So based on this question, you can know how that the cm can, and can also get the mass of the, if you have the C of the this matter, you can know the how mass drop into the without the. Okay, that's all for this question. I think that's all for now. For this, hope that you can answer the question very well soon in your NTEM exam. It's nearly the 1 hours class. Okay, thank you very much. See you soon in the NTEM exam. Thank you. Bye bye. Assalamualaikum.